Today we're going to start talking about carbohydrates. And this is, broadly speaking, the field of biochemistry that I got my PhD in. In fact, next week we'll see, I'll talk about allolactose, which was one of the, we'll see some research that I did. I'll show you a little bit of the work I did. Carbohydrates. So when I say carbohydrate to you, what's the first thing that comes to mind? I imagine for many of you, it's going to be sugar or pasta, for example, or bread or honey. We see a picture of honey here. Any of the things that are popularly associated with carbohydrates, and indeed, they are all carbohydrates. Throughout the course of the next four lectures, I'm going to try to get you to see that that's only a narrow band of what carbohydrates actually are and what they're doing for you, providing energy. They do a lot of other things. And I'm going to set the molecular groundwork for a little bit more nuanced and sophisticated understanding of what carbohydrates are. And there are at times during this where we're going to be getting into the structural biology of carbohydrates, that is, what their topology is, what their three-dimensional structure is. And it may seem like, wow, this isn't really, doesn't seem like this is directly relevant to understanding food and the chemistry of food. But be patient, stick with me, and I hope to close the circle for you so you do understand these connections. All right. So carbohydrates themselves, carbohydrate chemistry is actually a very small portion of the field of biochemistry. Most biochemists, when you talk about biochemistry, they think of protein chemistry. We spent a lot of time talking about protein, not so much talking about enzymes. I did last time, but the action of enzymes and the reactions they catalyze, that is, and the genes that encode those enzymes, that's the bulk of what biochemistry is, all right? Or at least as it's practiced. However, despite that, most of the planet, most of the biomolecules on Earth are actually carbohydrates. So, it says 85% of the dry biomass on Earth. When you go walking in the woods or through a field of wheat, most of what you're looking at is carbohydrate of some form or another. And the reason that so many people study proteins and carbohydrates do get studied, but not to the degree that proteins do, is because of the unique role that they play and some unique characteristics that carbohydrates have that make them both challenging to study and because of those challenges, the possibility for rapid exploration, rapid understanding of carbohydrates isn't the same as in protein. So the work in carbohydrate chemistry is a slow, kind of plodding endeavor. All right. Carbohydrates are probably, beyond being the most abundant biomolecule on Earth, they're also most evolutionarily ancient. They were probably the first biomolecule on the planet, even certainly predating protein. And they say that the first enzymatic activity that happened on Earth was actually by what are called RNases, structured enzymes. So these are enzymes not made of amino acids. They're enzymes that are made out of RNA. But you can't have RNA without carbohydrates, because ribose, which is a carbohydrate, is part of RNA. It's the ribo in the ribonucleic acid. Carbohydrates date back before life on Earth, of course, about 3 billion years ago, to these reduction oxidation cycles that happen, these redox cycles that happened on the Earth, associated with the different oxidation states of iron. So we had light from the sun on the left-hand side. You see there the H nu of about 400 nanometers. That was a particular wavelength of sunlight, was driving these redox cycles, where carbon dioxide in the atmosphere plus acid, some sort of acidic content of the primordial broth that was there. This is back when the Earth was a rock, right? There was no slime anywhere. There was no chemicals to be slimy, which are the sliminess that you see, the biofilms. Those are because of carbohydrates. This is before that. It was rock, and water, and some very simple organic molecules. Carbon dioxide in the atmosphere, along with protons from an acidic broth that they were soaking with, were caught up in this oxidation cycle with iron. And iron was reduced, and we got the fixation of carbon dioxide into aldehydes. So we have CH2O, and the byproduct was water. And this very simple organic molecule, the acetone, with time combined with other simple organic molecules to form carbohydrates. One of the ways that they know that this happened was what's called the banded iron formation. So in the geological record, there are these, at the very, if you dig down beneath the oceans, there are these geologic formations that are these banded colors. And we see in the upper right-hand corner a picture of a rock from the banded iron formation. That's a geological formation about 3 billion years ago, where you see layers of iron 2+, and then another layer of iron 3+ on top of it. Maybe each of those bands were 1 million years in between each of them, what have you, sort of depicting different epic ages of early, I guess, prebiotic chemistry. So let's fast forward 3 billion years. So the very simplest carbohydrate, any carbohydrate, in fact, the name. Let's just dissect the name. What does the name mean to you when we dissect that name? Carbohydrate. Carbohydrate. What would that suggest? Yeah, exactly. Yeah, carbon that was hydrated. And indeed, when we look at the empirical formula of carbohydrates, the ratios of carbon to hydrogen to oxygen is 1 to 2 to 1. So the overall formula of a carbohydrate is CH2O. And then there's a subscript N, denoting the length of the carbon chain. That carbon chain could be 3 carbons long, right here in glyceraldehyde. So there's going to be 3 carbons down the central backbone of glyceraldehyde. There are 3 oxygens, you see. And then there are 1, 2, 3, 4, 5, 6 hydrogen. So that's a CH2O, and the subscript there is 3. So that could be a C3H6O3 would be another way to write that. And glyceraldehyde is just an oxidized version of glycerol. Glycerol itself is a polyol, just an alcohol that has 3 OH groups, 3 hydroxyl groups. And glycerol is a lubricant. It tastes a little bit sweet. It forms the backbone or the junction point in a triglyceride. But we take glycerol and we oxidize it, one of those alcohol groups, to an aldehyde, and we have the basic carbohydrate. And so every other carbohydrate that we see is essentially going to vary by the number of those central carbons. We see the carbon in the center has one hydroxyl group attached to it. It's attached to the carbons on either side, and then there's one other hydrogen. The number of identical carbons to that carbon in the center is going to determine the length or the size of the carbohydrate. But on one end, you're going to have an aldehyde or potentially a ketone, but we'll get to that. And on the other hand, you're going to have what's called a hydroxymethyl group, which is basically that OH, that alcohol group attached to the 2 hydrogens. So that's the basic structure of a sugar. All right, and so let's look at the tree of different sugars. All right, each of these sugars on this aldose tree is what we call this, are monosaccharides. So a monosaccharide is another way of saying a simple sugar. A simple sugar is a single sugar chain, not attached to anything else. We call it mono, meaning one. Saccharide is another word for sugar, coming from the Greek. So we're going to classify these monosaccharides based on the number of carbons in the backbone. I showed you glyceraldehyde, and we call that a triose. Any word with O-S-E on the end of it, ose, designates a sugar. So sucrose or glucose or fructose, those are all sugars, O-S-E on the end of it. A triose is a sugar which has 3 carbons in its backbone. And so the molecular formula is going to be C3H6O3. We saw a picture of glyceraldehyde. In fact, I will have a glyceraldehyde here. You guys pass that around. Just take a look at it. A tetrose, tetra is the prefix, the Greek prefix for 4. Or is that Latin? Maybe it's Latin. No, it's Greek. Pardon me. Tetrose is a 4-carbon sugar. So its molecular formula, adhering to that CH2O format, is C4H8O4. And the N, the subscript N in a tetrose, is 4. And there are 2 potential tetroses. We have erythrose and threose. Now, if we add another carbon to the backbone, it's going to be called a pentose. Pent is the prefix denoting 5, and we have 4 of those. We have ribose, arabinose, xylose, and lixose. So this tree is expanding geometrically here, isn't it? By a power of 2 each time. And hexose has the prefix hex, which is 6. So there are 6 carbons in the backbone. This way of writing the sugars out is called a Fischer projection. We're going to see what that means a bit more in a couple slides from now. And in the hexoses, there's going to be some carbon and some sugars that you recognize. So, for example, down there on the bottom, you see glucose. Perhaps some of you have heard of mannose or galactose. but certainly you've all heard of glucose. There's also ribose, I've already talked about today, that's part of DNA. And then glyceraldehyde, we also spoke of. These are the more common sugars. The other sugars that you see here, some of them occur in nature, others do not. None of them occur to a very high degree. None of them occur to a very high degree in nature. Another thing you'll notice about this diagram is when you look at the names of them, for example, glucose in the bottom, you see a D and then parentheses a plus sign and glucose, or at the top D-glyceraldehyde. The D stands for dextrorotary, and we're going to talk about what that means, but essentially that's a way for us to designate the spatial structure, what's called stereochemistry, the three-dimensional arrangement of the atoms about the carbon, and specifically the carbon that's in the red box. So we're going to define what stereochemistry means in a few slides here, but the D refers to the carbon that's surrounded in that red box. And let's just look at that second line there, the tetroses, rithrose and threose. They're both D sugars, so they have the same arrangement about that carbon in the pink box in those two structures. However, if you look at the carbon up the chain from it, the arrangement of the hydroxyl group, the OH alcohol group, and the hydrogen around that carbon is different between the two of them. So you see the permutations expand. There's a binary choice about that carbon, the way that you can arrange that hydroxyl group. And so the geometric expansion as we go down the tree is a power of 2. Have I lost anybody with what I've said so far? Don't be shy. You guys following it? So I want to try to explore this idea a little bit more. So 2, 4, 6, 8, 10, 12, 13. So why don't we break up into groups of 2 and 3? I want 5 groups. So just 2, 4, 6, 8, 10, and then the 3 of you. What we're going to do is I'm going to give each of you a set of these molecules. And I want you to take a few minutes, just a minute, or look at. I want you to look at the set. So 3 of you gather. You're with. Take a couple minutes and look at them and try to describe in words as best as you can the relationship between those. Okay? Come up with a statement, some kind of a statement that you think describes the relationship between those two objects I've put in front of you. All right? Try to come up with the most succinct possible statement. Most possible describe. Who you guys got a statement, you think? Yeah. Who's still working on it? Seems like much everyone's there. Um, let's hear it. I want. So we have 5 groups. Um, let's just go around. What was the statement that you have that describes them? How would you describe? Okay, they're mirror images of one another. So um, is the relationship so these are mirror images. Is the relationship between these the same as that? Okay. What did you guys have to say? Okay. What if you switch the blue and the green? Would it? What did what did you guys come up with? Okay, they're symmetrical but different arrangements. I need something more. So these guys were on to something. Were they wrong when they said that they were mirror images of one another? No, they are mirror images of one another. But just saying that molecules are mirror images of one another isn't capturing everything, because these are mirror images of one another as well. There are 5 different elements to it, okay? But I could put a methane in front of you. Or better yet, I could put an Fe3 molecule that has 5 elements around it, and it may not be the same relationship. I don't have my bag of elements here, but I need, there's like some other thing. Like these guys started off strong, but there's some other aspect of this. What did you guys say? You're with them. What about you guys? Okay, they're somehow connected differently. They're connected differently, but they are mirror images of one another. All right. Well, what is the difference between a set of water molecules here that are mirror images and that set of mirror images? I have a mirror image of each other, but then I can take that mirror image and superimpose it on the original image, can't I? So that they're indistinguishable. I can superimpose them so that they're indistinguishable. Can you take those mirror images of one another and superimpose them on one another? No, you can't directly map them on to each other. You guys were talking about symmetry, weren't you? The truth is the word symmetry is good here, but it's because the relationship between these two things break a symmetry. They break symmetry. If you try to superimpose them on one another, they are not symmetrical to one another. They're symmetrical about the mirror plane. All right. Let's think about this. This guy here, named Emil Fischer, was thinking about this a lot at the end of the 19th century. And he needed a way, he didn't have these things. He needed a way to depict this problem. There's a problem here, and he wanted to describe it. You guys are all really smart students. You got into Colby, but you also kind of struggled to come up with an adequate description of what the relationship was between. So he had that same struggle, and he started breaking it down into the practical problem of how do we even write this? How do we depict it on the page? So he came up with what has become called the Fischer Projection. And if you were to have one of the things in front of you, so one of the groups had talked about how there were 5 elements. That was Sunny. You had said there were 5 elements in it, right? So 5 elements can arrange themselves in what's called a tetrahedron with the 5th, tetra meaning 4, hedron, 4-sided shape with a 5th element at its center, all right? And if each of them are different, or at least the A, B, C, and D are different, the center atom doesn't matter. If they're different, then there's some non-superimposability in the mirror image, mirror images that you can have. He wanted to describe that on a piece of paper, so he has this Fischer projection, where if you take, so take one of the things in front of you, and you can line it up so that maybe the silver and the white are the A and the B, and they're pointing away from you. The 2 of them are pointing away from you in a vertical plane. And then the C and the D, maybe the green and the other colored one, are pointing towards you. And he depicted these with a dark, a solid triangle coming out from the center as coming out of the plane of the board towards you, and the dashed lines going into the board away from you. All right. So the blue ones in the blue circle and the blue dotted circle is above the plane, and the red is below the plane. This guy he had a pretty interesting life. I'll just give you a little bit about his life, which I find interesting. So he won the Nobel Prize in 1902 for his work on carbohydrate chemistry. He was really one of the first true carbohydrate chemists. He was, him and his family were deep pacifists. A lot of his interest in carbohydrates came from spending a lot of time in an agrarian context, out in nature in the woods, and wondering, I told you 85% of the biomass of Earth was carbohydrates, and he certainly appreciated that aspect. Despite the fact that he was a pacifist at heart, his wife died after only being married to him for 7 years. In that time, she was able to bear him 3 sons, which were of great pride and joy to him, but the first was killed in World War I. The second committed suicide because he also was a pacifist and was forced into compulsory military training by the Germans in World War I, and he didn't want to fight. And then Emil Fischer himself, after having lost his wife and 2 of his 3 sons, committed suicide himself at the end of World War I. Of personal note is that this guy's 3rd son fled Germany and became a professor at UC Berkeley of carbohydrate chemistry, who turns out to have been my academic great-grandfather. So he was my advisor's advisor's advisor. And most carbohydrate chemists that you see out there descended, not most, but many, a large portion, were trained by this guy. So let's look at glyceraldehyde. Here are two glyceraldehydes. And I'm going to give this to George, and you can take a look and gander, see if you can grok the difference between those two and pass them on. The same kind of problem presents itself in glyceraldehyde as presents itself in the little molecules that I handed out to you. And it's not around the carbon that is in the carbonyl group, in the aldehyde group on the top, and it's not in the hydroxymethylcarbon on the bottom. Or is it? I don't know. You tell me if you don't agree. Do you agree, George? Where's the problem in there? What's the relationship between those two? Yeah. Yeah. So this is what Fischer was struggling with. How do we describe the relationship between these two molecules that you get a bunch of glyceraldehyde, you make some glyceraldehyde, and it's a mixture of these two different chemicals. It's a mixture of these two different chemicals. Before I leave this slide, a couple other things about this guy. He was also the first to chemically synthesize glucose and fructose and mannose in 1890, starting from glycerol. He took glycerol and was able to make glucose out of it. And he established the stereochemical configuration of all of the known sugars that I already showed you on that tree, and foretold the existence of others that weren't known to science at the time. So he used this Fischer projection convention of drawing to try to describe the structure of these sugars that he found, the stereochemistry of them. All right. So I'll stop baiting you guys any longer. They are mirror images of one another, but they are importantly non-superimposable. You can't map one onto the other. I've already said that. And the relationship between them we call chirality. Chirality is the property of something, like symmetry is the property of two things being symmetric about a plane. Chirality is being mirror images of one another that are not superimposable. So, for example, the most familiar non-superimposable mirror images that you may have are your two hands. Your hands are mirror images of one another, but they're not superimposable. You can't map one hand onto the other. All right, they're mirror images, and your hand would be chiral. The relationship between things that are chiral is they're called enantiomer. So the two glyceraldehyde molecules that I handed out there have different stereochemistry, different chirality about that central carbon. And if you stare at them long enough, you'll see it. That chirality makes them enantiomers of one another. Enantiomers, or chiral molecules, are what are called optically active. And we'll see what that means. And optically active is a practical description of something. So when you have a chiral molecule, they're able to rotate polarized light. And we'll see what that means in the next slide. So optical activity is the ability of a chiral molecule to rotate the plane of polarized light. What does that mean? We'll get to that in a sec here. Let's look at the structure of glyceraldehyde. So here's a molecule of D-glyceraldehyde, and if we look at that center carbon, ignore everything else. Imagine that all this stuff over here is the same as one of those green balls on your the thing that's in front of you. And maybe this is one of the silver ones, and this is here's a white one, and maybe this is one of the colored ones. 4 different groups that are each different from one another. Right? They're each distinct around this tetrahedral carbon. That makes this that makes it optically active, and we'll see again in a moment what that means. It means that it's going to have a chiral enantiomer. There's a mirror image of this that could have any 2 of these 4 things around that center atom just switched, and it will make it into a non-superimposable mirror image. All right? And if you switch 2 more, then you're going to switch them back to the identical molecule once again. So there are exactly 2 enantiomers in each of these situations. What about this carbon? Is that carbon chiral, chiral center? What do you think? Nick, take a guess. Why not? Okay, why? Yeah, why? Okay, so let's imagine, let's just consider this carbon here. We have these different, there are 4 different groups around it. Why is he right, or is he right? Who's getting flummoxed by the puzzle? The carbon's in the center. That's not what's controlling this, though. Why is this carbon not a stereogenic center? I'll tell you, it's because these two substituents on it, these 2 things that are stuck to it, are the same. They're the same. There are not 4 unique things around that carbon. There are only 3 unique things around that carbon. All right? So if I were to take a mirror image of this, it would look like, and imagining this wasn't, not worrying about the stereo properties of this one, just thinking about the stereo properties of this one. This mirror image would be superimposable on this one. And you don't have to take my word for it. You can hand those around and see how that's the case. The only stereo center is this one in the center that has 4 different types of substituents on it. All right. So optical activity. These chiral molecules, we can take light, and light is a wave, and those waves can be, as a wave goes, it can go up and down, or it can go side to side, or it can go in any direction along the path of the light, and that's what I'm depicting in the normal light portion of this picture. But I can pass that normal light through what's called a polarizing filter. Does anybody ever, does anyone wear polarized sunglasses? Okay. And have you ever taken 2 pairs of polarized sunglasses and put them, how do you, okay, I'm answering my question. How do you tell if sunglasses are polarized? So light from your cell phone or computer screen is polarized, and if you orient the polarizing filter on your sunglasses perpendicular to that polarized light, it'll block out all of the light. Likewise, if you take the 2 different lenses of different polarized sunglasses, or you pop the lens out of one side of your sunglass and you put it at 90 degrees to the other lens, the polarizing filters will be at 90 degrees to one another and will block out all the light, and it'll go totally dark. So when you take two lenses and you turn them, you can see the light go from bright to dark. All right, so we polarize the light that's coming through, and as that polarized light passes over a chiral molecule, it's going to bend the light in one direction. All right, it's going to, depending upon the molecular particulars of the red, green, blue, and black substituents around that chiral center. Say it bends that light by 20 degrees. All right. If the same polarized light goes around the chiral enantiomer, it's going to bend the light by 20 degrees in the other direction. All right? So you can distinguish chiral molecules by the direction of the way they bend light, polarized light that passes over them. This was the plus that you saw in the tree of hexoses. Plus means it turns it to the right. Dextrorotary means turning things to the right. Levorotary means turning things to the left. But I have another slide that will describe that better. All right. Oh, here it is. So here is the two glyceraldehyde molecules that Sunny has right now. And the only chiral center in them, she's convincing herself that I'm not lying to you by looking at it, is that central carbon. It's the only carbon that has four unique substituents to it. We have one that bends light to the left. We call that levorotary. And one that bends light to the right, dextrorotary. So there are two different glyceraldehydes out there. The thing that's interesting is chemically they're the same. They have the same boiling point. They have the same freezing point. They react with other molecules in the same way. But they are non-superimposable mirror images. But they are not identical. That doesn't make them identical. And we'll see what the importance of this in a bit, right? Because nature has seen fit to throw us for a loop here in the foods that we eat. Oh, is that it? There it is. Okay, so that's stereochemistry. That's what I wanted to get through today. We're going to pick up with Hawthorne projections next time and how these sugar chains can cyclize to form rings. Final on Friday, and lab should take you maybe a half hour, I'm guessing.